Hey, so let's talk about perceptrons today. Perceptrons are essentially a one layer neural network, so this video is going to take a little bit more explaining than my previous ones have. But we'll reuse some concepts, and I'm really excited to show it to you. Let's get right into the gameplay, and then I'll show you how to build.
All right, we are getting into neural networks. So let's do this. ML emotions recognition. Emotions. Yeah, so I managed to make my computer detect a cat. That beast is a complicated soul. It definitely has more to tell. Maybe it's time to go next level and start recognizing emotions. Ever heard of perceptrons? They were invented in the 60s to recognize written text. Everyone knows everything invented in the 60s is awesome by default. Helix, rock and roll, lava lamps. Also, you can maybe switch to dogs instead of cats. Decision trees works like a magic for my Pluto. You can also hit the store and get that random forest node. The forest is more effective than just one tree, you know. Right, we're getting into perceptrons. Something completely different. Perceptrons can actually learn and improve. Bad news, they also make a ton of errors along the way. This percentage of errors is shown in this icon. So we've got a new button, this training button, along with the test run and save. So we have to train and then test, and if it doesn't work, we may need to retrain. So, okay, the Mark 1 Perceptron. Game, Perceptron reduces the amount of errors while trying to predict the shape of elements. In test run, Perceptron only predicts shapes. Rosenblatt's Perceptron is used in Mark 1. This Perceptron could recognize only simple linear dependencies. It was enough to recognize English letters. That's nice. Oh, looks like there's a whole course here. So here we go. Mark 1 Perceptron. How it goes circle to circle, square to square, and triangle to triangle. Take note, this takes 6.93 seconds, but it has a 75% error rate. Let's train it. Turn it up. It's going to increase its error. You'll notice it's not very accurate in any of these. So minimum margin of error, there's nothing more we can teach them. That's important. It's only 80% accurate. So you'll notice over here, our required accuracy has changed from 100% to only 60%. So let's see how it works. Nice, nice. It's 100% accurate so far. Oh, no, it's not. It missed a square and it missed a triangle. Looks like it missed two triangles and one square. But that's still good enough. We're in a couple times for luck. So the text recognition. We are aware that you were able to create a text recognition system based on the Rosenblatt Perceptron. This is a reCAPTCHA company. We need a similar system that would also be able to distinguish vowels from consonants. Ooh, this is simpler, but more accuracy is required. This is really cool. So yeah, we'll open it up and then we can talk about it more. The Rosenblatt Perceptron. The first Perceptron was invented by Frank Rosenblatt in 1957. You'll notice it's before the decision tree in 1966. Frank created Mark 1 in 1960. Mark 1 is a perceptron machine that can recognize English letters by their shapes. So handwritten letters. Let's do this. Interesting. Oh, and that just stops us straight up. Just stops us. Okay. Let's do this more. Okay, so we've got a minimum margin of error. 30. Why don't we have the triangles here? Let's see how that works for us. 10 more seconds. Hey, that worked. So let's go back and let's talk about how I came to this decision. So we're looking at this. This was 60% accuracy required before. Now it's 75% because we want to distinguish not just between words, but also between vowels and consonants. So the parts of those words. We're using this perceptron, of course. And you saw when I was training, if I didn't have the triangle going anywhere, it just stopped everything up. We want triangles on both sides, so it didn't matter which one we had the triangle going to, it would still help us. You'll notice the number that we need, the quantity, occupancy, 18 up on the top and 30 down on the bottom. So I put the triangle going, the same one that required more. This works. Yeah, we've already tested it. It's gonna work. Even though the accuracy on that bottom one is going down, we still got an 87% accuracy in total. We needed 75, so that's what it's. Now let's go to parallel calculations. The scientific center, their current programs are underperforming. Can you parallelize our calculations? Data, your nodes need computing server. So nodes require more server. The more servers you use, the more expensive it becomes. So load balancer. A load balancer in the real world is a device that distributes network or application traffic across a cluster of servers. Load balancing improves responsiveness and increases the availability of applications. But it increases cost as well because you need two copies of the same distributed system in order to get it across. Balance both of the output streams. And you'll see just it doesn't do any sort of sorting. One goes one way, the other goes the other way. That's it. That's why you need two copies of whatever system is going to be on the other side of the load balancer. There's more stuff about here. I mean, I know there is. Increases server cost base. We only have 172 left. So another text. I love this course. No way I'm changing that. We want to join a startup. We don't have money to join a startup. Let's do this dairy products. $900. Hello, my name is Sam. I own a dairy products factory. My dream is to make the very best goods on the market, and that's impossible without high accuracy and fermentation processes. All right, off with the fancy words. I want a program that will judge the quality of product by its ingredients. We often make mistakes when doing it manually, and a lot of our products never leave the factory since the market is defective. We have data. We need the algorithm. I wish that all wheel drops were like this. But they have all the data. It's already readily available. I don't need to find any of it. I don't need to clean any of it. Just train my model and then freaking just go. Easy. We needed 2 nodes there. I don't know what N1 would even use the second node for. So they figured out a better way to speed it up so you don't cut it that close. I don't hear construction. Letter from a friend. Hey, what's up, buddy? How are you? Listen, I know I wasn't paying you for quite a long time. I'm very grateful you weren't demanding a paycheck for so long. But in debt, even your friend is not cool at all, right? Therefore, take this money you honestly earned. Thank you, friend. Cash. Oh, that's so nice. Metal Gear Construction. We produce fittings and supply raw materials. We are especially proud of our high standards of quality. At the moment, we're seeing more new orders. We're running late with deadlines. Algorithm is required that will analyze the quality of raw materials and discard poor quality or before it leaves the conveyor. Anyone else is waiting. It takes way more time than we can afford. Perfect. Okay, so let's first off, let's just freaking train this. Train. Oh, okay. Two of these. This one's already trained. Oh, okay. So green. Here. Here. We want blue triangles. Nothing else. Green triangles. Nothing else. Aesthetic, we want red. Squares and circles, but not triangles. Let's test on this. We should get around 80% accuracy. Wait, it did not go fast enough. 34.1 seconds. Should be able to do this only for 8 seconds. So, okay. Let's flip this. Delete all of these. Perfect. Let's start with this since it's the slowest one. You'll notice we only need some types of red, but blue and green are the same shape. So let's do red up here, these shapes up here, just red and blue. So let's go here, and then both the greens and blues go in the trash. Perfect. Here. So we're using only 5 out of our 7 nodes, but this should handle it faster than the previous method. Oh, I was so absolutely wrong. This handles it way slower than the previous method. Please delete. So we got red, green, and blue coming out here. Why don't we just freaking plug the red in? Green and blue. This is one word so it doesn't get clogged up. Green and blue, we want only triangles. The rest of it in the trash. So hopefully it will help us keep our accuracy up, but also make sure that speed goes up. Yeah, there we go. There's our gold. Notice we had to make a compromise, understanding that there were 20 red circles and squares and only 15 triangles. That means so out of the 35 reds, we're going to get an accuracy of about 60%, barely more than half. We're able to pad that with the green and blue triangles, and just hoping that these Perceptrons with their 80% accuracy wouldn't put too many of the green circles and squares in there, because there are a lot of those that could hurt us. All in all, it did work. We ended up with 77% accuracy. It works now when we're faster than 20 seconds. Oh, that's fantastic.
Okay, so we've gone over Perceptrons, what they're for, when to use them. Let's get into building them right now. And let's create a new file within our folder called perceptron.py. Now for this, we're going to need torch. If you don't have torch, please head to pytorch.org. I'm putting it in the video right here. Head to pytorch.org. They've got great instructions to get everybody up and running. Let's create our class, Perceptron. We are going to inherit from torch.nn.module. I've told you guys in the past with these videos, I've had a lot of debate about whether I wanted to teach you how to make stuff from scratch or teach you how to make stuff that's functional. And I'm always leaning towards that teach you how to make stuff that's functional side of things. So let's make our little doc string. One linear layer network. All right, now let's get our init function for whenever we're initializing. This will take self, and this is going to take an input dimension. And that input dimension, for anyone that's wondering, represents how many features we want to measure. We're going to call the Perceptron class as soon as it is instantiated, and we are going to initialize on that self call. Okay, and our one linear layer is going to be fully connected. It's torch.nn.linear, and it's going to take our input dimension and 1 as an argument. So this is our Perceptron. This whole thing right here, one line of code. I know that TensorFlow has something similar for it if you like TensorFlow. So our forward function is going to take self, obviously, and it will take, we're going to call this xdim, and we will return torch.sigmoid self.fc1, and we're going to do that on xdim. Perfect. This is the whole thing. This is the Perceptron itself, and the rest of this is just defining the behavior of what happens when we call it. So now let's get into learning about what this Perceptron does. And to help me do that, I got permission from O'Reilly to use this chapter from one of their books. This is a deep dive into supervised learning. I strongly recommend, if you have the money and the time, go take a look at O'Reilly if you're interested in coding, if you're interested in machine learning. And just because I wanted to showcase what we just built, this Perceptron.py right here, we're going to import it and use our Perceptron that we just built within their notebook. So here's some functions that they have. Let's take a look right here. This is our data set. Let's pretend for this that stars are people who get into MIT, circles are people who don't get into MIT. Something you don't have to do in the game, but you do have to do in real life, is setting all of these variables. The learning rate, which controls how big of a step we take every single time as we try to draw a line between these two categories. All of our data is going to be put into some n-dimensional mathematical space. We need to create numerical data so that we can make tensors out of that data. Tensors are essentially matrices that include information about where in the space it fits. And our machine learning algorithm, its task is to draw a line and then realize that that line is very wrong and take a small step in the right direction, draw another line, realize that that one's wrong and wrong and wrong and wrong and wrong until we're getting closer, and maybe that one's right, but it's a little wrong on the other side, and so it has to go back and adjust until it can draw the perfect line separating these two categories. Let's watch our Perceptron that we just made train and then create new lines. That was awesome. So it starts with this line that's terrible, and it gets a little bit better. Some stars are turning white here. That means we're getting them right. You can see that. You can see even the margins of the line are getting smaller. Too far, too far. And you can see here is where machine learning models excel that decision trees can't. I told you last time, decision trees really excel when there is an absolute boundary between your categories. Otherwise, your accuracy is going to fall really greatly because decision trees aren't meant for generalization on these subjects. If you have a hard and fast line between them, between your categories, you maybe want to look at using a decision tree or something that doesn't take as much computational power as a machine learning algorithm, because this is made to be able to generalize over overlapping categories. So let's take a look at our final line that we were able to draw. So this would be a perfect data set, and this is our data set. This is meant to generalize over this very large data set. So now what do we do? You know, this is where most machine learning tutorials that I've taken, at least myself, have ended. that, we got our model, it trained, it has a 97% accuracy or something of that sort. Now what? This is where we get into saving that model the way that we do in While True Learn, and using it over again and training it on different data sets and fine-tuning it and getting a lot of use out of this. So let's save our model using this torch.save, and we save the perceptron.state dictionary and we give it a name. So from Perceptron import Perceptron. Let's go over some different customization points that we can do with perceptrons that are not mentioned in While True Learn but are very important in real life. First off is activation functions. So let's go over some activation functions after we've saved this. This first one that we have is a sigmoid. This is what a sigmoid looks like mathematically. It's 1 over 1 plus exponential negative x. So e to the negative x. And you can see what this does is it squishes values into a space between 0 or very close to 0 and 1 or very close to 1. Let's move on. We have our tanh function, which also squishes things, but a little bit cosmetically different. It squishes between 1 at the top and -1 at the bottom. So we have a slightly larger space. You can see this line is a little bit steeper to accommodate more value. It's not extremely different to the sigmoid though, and this is how that's expressed. This is probably the most useful of all of these in the modern era. This is called the ReLU. Some people pronounce it ReLU, some people pronounce it ReLA. You can pretty much pick how you want because it's an acronym anyway. Here's what it is mathematically. It's a maximum of either 0 or the point itself for every single point within our data. So it essentially cuts off all of our data at a 0. If we used a ReLU in our perceptron, which we aren't, we're using a sigmoid, if you remember that. So here's our torch.sigmoid. We could use a ReLU, we could use a tanh. This provides you with customization for that. Our forward section is where we put our activation function to make sure that it's training the way that we want it to train. So if you change this to torch.ReLU, right here, you can do that. There's something called vanishing gradient if you're interested in learning about that entire problem. So they came up with this, the parametric ReLU or the leaky ReLU, which as you can see, here's the 0 origin point. It allows some negative values, but it's definitely still clipped. So softmax is useful for giving us a list of probabilities that all add up to 1. This is normally used at the end of a neural network. And it's really useful for identifying how did your neural network classify different probabilities. Our optimizer that we're using is Atom. I would recommend before you get into optimizers pretty deeply, just use Atom every time unless you're specifically told to use a different one. Here are the first two loss functions that I'll introduce you to: mean squared error and cross entropy loss. Both of these are meant to show us the difference between the answer that our network guessed and the real answer so that we can then change the network, change those weights. See in this trained model.pth, these weights, we want to change the weights as it learns to make sure that it's learning the right thing. But for us, because we only have 2 classes in these examples, we're using binary cross entropy loss, BCE loss. This is what happens when we print out our class, the Perceptron class. We get a good look at all of the layers within. Here's our data. So we're grabbing that right here. We're getting data target from that same get toy data. But you'll notice instead of calling it on 1,000 different batches, we just want to test 1 data point, so we did 1. It's important to understand the shape of the data because, like I said before, this shape is essentially the matrix, which within our n-dimensional space, in this case it's 2-dimensional space, it has information about where our data point actually is so that our machine learning model can draw a line. Now again, this machine learning model that we trained, our Perceptron, we've already trained it, so there's already a line there. Now we're checking whether or not that line it drew is correct. That's why here we're putting it into evaluation mode. This is how you load your Perceptron after you have trained it. So you instantiate a new version of the Perceptron with the exact same input dimension as the trained model you're trying to load. You then load the state dictionary of the file that we have. So we have our data, we have our target, and we have our prediction. Our data looks like this. Our target looks like this. Our guess is 0.133497 and on and on. How do we make something good out of that? How do we make something usable out of that? Well, we can use some sort of a vectorizing function in order to essentially do what a sigmoid would do. Or I guess compound the results of a sigmoid is push it to either a 0 or a 1 instead of having it be somewhere between 0 and 1. Which that's what I have it doing here. If it's greater than 0.5, guess what? It's a 1. And if it's not, then guess what? It's a 0. In our case, it guessed a cat, and it was right. So let's talk about applying this other places as well. This is another thing that I wrote today that allows us to use the Perceptron on our color CSV. Again, we always have to do from Perceptron import Perceptron because we just wrote that. And then you may recognize this code. This is just copied and pasted from our decision tree example. Now keep in mind there are only 30 data points here, so we're not going to get a really great train, but we will be able to get something out of it. So we have our Perceptron, which is instantiated with the exact same input dimension as before. We are loading our Perceptron. We're putting it in training mode. Here are our optimizer and our binary cross entropy loss, the same as we had before. And basically what we're doing is we're grabbing 1 point of real data for every number of batches we have, and our number of batches is 1. Then we'll switch it into evaluation mode, and we'll do something similar. It will receive a list of 2 numbers between 0 and 2, and here is why that is not as good for machine learning. Is it's very easy to write something that's way less computationally heavy to predict whether or not it would be good. If it's a straight A red student, then they got in. If it's not, then they are not in. And I have it saying Cornell instead of MIT. I hope that I'm not offending anyone who went to Cornell because I think it's a fantastic school. I was just kind of making a joke out of this as I was writing it. So let's run this. So this is the choice that it got. It got a 1 and a 2. Here's the resulting tensor from it, where it's predicting 0.06% chance that they got in. So guess what? It guessed Cornell, and it was totally right. Let's run this until it gets it wrong. Here it goes. So turns out, in our data set, the fact that you would be red is more important than the fact that you got good grades. That's something that it learned. This is something that entire careers are based off of. It was a C red student. So to our model, based on the data that we gave it, it's more important that a student falls under that red category than they had good grades. That's really interesting. I'm not going to go any further into this. If you have more questions, please let me know in the comments. I'll be happy to answer as much as I can, but I'm going to be working on the next video in this series. A little bit of an update on the channel. I have a merch store now. Please feel free to visit that. I'll put it in a text blurb right here above my finger. It's streamlabs.com/imjones/merch. Please feel free to visit it. And please feel free to like and subscribe. It would really help out the channel. Thanks, everyone.